Hi and welcome to this tutorial on empirical and molecular formula. So in the previous tutorial, we learnt about the ideal gas equation, so PV equals nRT, and its use in calculations. So in this tutorial, we're going to look at lots of things, all to do with empirical formula. So you can see here quite a lot of different types of calculations. So the core concepts we're going to be studying in this tutorial are molecular formula, empirical formula, and empirical mass. The molecular formula, you will have come across this before. It is, of course, the actual number of atoms of each type of element in a compound. So if we just ignore what I've got drawn here, if we have hydrogen peroxide, so H2O2 is the molecular formula. It's telling me I've got 2 hydrogens and 2 oxygens in that molecular structure. And a certain number of what we call empirical units make up that molecular formula. So that's the molecular form of hydrogen peroxide, whereas the empirical formula is HO. The empirical formula is the simplest whole number ratio in the molecule. So the empirical formula being HO tells me that for every 1 hydrogen, I have 1 oxygen. So that's our empirical formula, and that's our molecular. And for some molecules, their empirical formula and their molecular formula are the same, but for lots of molecules, they're not. So like I said, the empirical formula is the simplest whole number ratio of atoms of each element in a compound. So I've got another example here. I have got C4H10. So I've got butane, that is my molecular formula, but we can also work out the empirical formula. So I can look at this and say, well, that's a ratio of 4 to 10, and I can just simplify that down. My ratio of 4 to 10 can be simplified. I can divide both sides by 2, so 2 to 5 ratio. So my empirical formula could be C2H5. That is the smallest whole number ratio. The empirical mass is the total mass of all of the atoms in the empirical formula. So for hydrogen peroxide, H2O2, its molecular mass would be 2 times 1, so I've got 2 hydrogens, plus 2 times 16, because I've got 2 oxygens. So 32, 33, 34, so 34. Whereas the empirical mass of hydrogen peroxide, the empirical formula is HO. So the empirical mass is just going to be 16 plus 1, 17. Pause the video and have a go at working out the empirical formula of these compounds. Right, so we've got water to start with. Now that is already in its simplest whole number ratio. For every 2 hydrogens, there's 1 oxygen. Then we've got glucose, a familiar compound that you will have come across a lot in terms of respiration, photosynthesis. So CH2O. If I times CH2O by 6, I'll get C6H12O6. So I'm just finding the simplest whole number ratio. Hydrogen peroxide, we did that earlier, HO. Butane, I can divide both sides by 2, so C2H5. And benzene, CH. I can just divide both sides by 6 effectively. You might wonder, why do we use the empirical formula? It doesn't seem that helpful, because in science we tend to use the molecular formula instead, especially for calculations. But it's helpful to understand, for us to understand the ratios of the different elements in the compound. So it tells us if a compound contains more than one type of element very quickly, and a molecule that contains more than one type of atom. So it gives us quite a lot of information. One of the key things you need to be able to do is to be able to calculate the molecular formula from the empirical formula and the relative molecular mass, the MR. So the key bits of information we need there, of course, the empirical formula and the relative molecular mass. So if we've got that data, we'll be able to work it out. So here's a practice question, because you may have done this before at GCSE. So pause the video, give it a go, but don't worry, I'll do a worked example as well. The first thing I'm going to do is to work out the empirical mass of the molecule. Okay, so empirical mass, and I've been given the empirical formula already. So I've got CH2O, so that's 12 from the carbon, 2 times 1 from each of the hydrogens, and 16, so that's 30. Then So I know that the MR is 180, it's given to me, and I know that the empirical mass, I wish there was a shortcut to write it, is 30, and I'm going to divide them. So I'm going to do MR divided by empirical mass. So 180 divided by 30, and that is going to give me 6 empirical units. So knowing I've got 6 empirical units, I can multiply my formula by 6. So CH2O times all of them by 6. So that would be C, I've got one of those, it's going to become C6. H, I've got 2, so times that by 6 is 12, and O times by 6 is 6. Now you're going to recognise this is glucose. You may also be asked to calculate the empirical formula using the percentage composition by mass. So in this case, you're going to be given the percentage by mass of the elements or percentage by volume of the gases. So we'll have a go at both of those types of examples. Here's a question. Pause the video and give it a go yourself, or wait for my work through. When you get given composition by percentage, it is good to imagine you've got 100 grams, because percent is 100% per 100. So if you've got 100 grams of this particular compound, it's unknown in terms of its formula, but you do know what the composition is. You know you've got carbon, hydrogen, and oxygen. So what these percentages are telling us is that if I had 100 grams, 64.8 grams would be carbon, 13.62 grams would be hydrogen, and 21.58 would be oxygen. So I can write that here. So by saying it's 64.8%, let's just change that into grams to make it so that we can calculate our answer. 21.58 grams. And, oh, that's my oxygen. Make sure that you read these carefully. 13.62 grams. Okay, then I'm going to calculate the moles of each of them. So the moles, N brackets C, that's me telling the reader that I'm working out the moles, is going to be 64.8 divided by the MR or the AR of carbon, 12. So 5.4 moles. My moles of hydrogen is going to be 13.62 divided by 1. So that's just 13.62 moles. And then my moles of oxygen is going to be 21.58. Now, although molecular oxygen is diatomic, so it's 32, when we're doing empirical formula, it's really essential that you're taking the AR, the relative atomic mass of oxygen, not molecular. So we're going to divide it by 16, not 32. We see a lot of students divided by 32. For empirical formula, we do not do that. So 0.349. Okay, and as a reminder, that's because we know that moles equals mass divided by MR, or AR in this particular case. So then we're going to work out which one of these is the smallest number. And you can quite quickly see that oxygen is the smallest number. So we're going to work out a ratio. We're going to divide all of these by 1.349. So I'm going to divide that by itself, which is obviously going to give us 1. I'm going to divide that by 1.349. And I'm going to divide this number by 1.349. And that's going to give us our ratio. So I annotated that on the previous slide. But if we do our 5.4 divided by 1.349, of course, I'm using the real numbers, not abbreviated. Hydrogen was 13.62 divided by 1.349, and that's 10. And then, of course, oxygen divided by itself, so 1.349 divided by 1.349 is, of course, 1. So therefore, it gives us our empirical formula of C4H10O. So you saw there, to work out my ratio, I divided them all by the lowest number of moles. So that's just setting up a ratio. Normally the calculations will work out as whole numbers, as you saw there, 4, 10, and 1. But sometimes you might get a 0.5. Remember, empirical formula is the smallest whole number ratio, so we can't have 0.5s or anything like that. So if you do come out with 3.5 as one of your answers, you need to times everything by 2 to get that up to 7. And remember, make sure you times all of your other moles by 2 as well. So it's got to be a whole number ratio. If they give you relative atomic mass or relative molecular mass values, it usually means you need to use them. So recheck your method if you've got to use them. So if you use the masses for ratios rather than the moles, for example, so check. Here is another question to have a go at. Pause the video and give it a go yourself. Okay, so let's calculate the number of moles of each of the products. So we know that moles equals mass divided by MR. So I'm going to have to work out the MR of my compound. So the MR of CO2 is going to be 12 from the carbon plus 2 times 16. So that's 44. And then my MR of H2O, now I know this off the top of my head, it's 18. So therefore, we need to work out the moles. Notice how I'm making this really clear to the reader by using sort of brackets and things like that. That really, really helps. And moles equals mass divided by MR. So 4.4 grams divided by the MR of carbon dioxide, which is 44. So that's 0.1. And then my moles of water is going to be my mass, 3.6 divided by the MR, and that's 0.2. There we go. First step done super quickly. Work out how many moles of carbon and hydrogen atoms there are found in the hydrocarbon. So in 1 mole of CO2, 1 mole of carbon atoms are present. Okay, so we can see that if I've got 1 CO2, if I pull all those apart, I would get 1 carbon for every CO2. Whereas with water, it's a little bit different. 1 mole of water, I've actually got 2 moles of hydrogen atoms present, because 1 molecule of water gives me 2 hydrogen atoms. If I had 10 molecules of water, I would count 20 hydrogen atoms. So we're just thinking about it in terms of counting the number of atoms per unit molecule. So 1 mole of H2O, Avogadro's constant, 6.02 times 10 to the 23, I would have 2 moles, 1.2 times 10 to the 24, of hydrogen atoms in that structure. Therefore, the hydrocarbon contains, we're going to do 0.1 times 1. So it's got 0.1 carbon atoms, or moles of carbon atoms, but it's got 0.2 times 2, it's got 0.4 hydrogen atoms. Because I've got 2 moles of hydrogen atoms that I've worked out in the previous slide, and I've got 0.2 for every 1 mole of H2O, I've got 2 moles of hydrogen atoms, so they're going to be times by 2. Therefore, the ratio of carbon to hydrogen is 0.1 to 0.4. So the empirical formula, which is the question, is CH4. That is the empirical formula, not necessarily the molecular. I'm not giving enough information, but that is definitely the empirical formula. And that's my answer. That's what I was asked to work out. Here's another empirical formula question, but we are going to be using volumes of gases here. So pause the video, give it a go, see if you can work it out yourself. You'll need to remember our gas law. So when we're at room temperature and pressure, 1 mole of gas occupies 24 decimeters cubed of space. Therefore, I can write out a basic formula for this. So I've got CXHY. They're placeholders because I don't know what the empirical formula is. I know it's reacting fully with oxygen, and I know it's going to make CO2 and H2O. So my volume ratio, what has it given us? So the same volumes of gases at the same temperature and pressure will contain the same number of moles. So I can just use, as a shortcut, the volumes as moles. Okay, so it's ultimately working in the same way. So I've been told that 150 centimeter cubed of CO2 is formed. So that's 150. And when 50 centimeter cubed of said hydrocarbon is burnt. So that's 50. And with 250 of oxygen. Ah, great. So I've got that information. That's what I know. And so I can put that into a ratio. So a molar ratio, 50 to 250 to 150. So if I divide everything by 50, surely that's going to get me an answer. So if I divide that 50 by 50, it's 1. 250 divided by 50 is 5. And 150 divided by 50 is 3. So what can I tell about my structure? It's going to be CXHY1, I can put in brackets in front of it, but there's no point, plus 5O2 makes 3 CO2 plus H2O. So we've got quite a lot of information here that we can work with now. So using that information, if I just write my structure again, it was plus 5O2 makes 3 CO2 plus H2O. Now I know that carbon is only found in one compound on the left-hand side and one compound on the right. So if I've got 3 CO2, X must be 3. So it needs to be C3 HY plus 5O2 and all the other information. So that's me having worked out that part. And then the next bit is, let's have a look at my oxygens. So 3 out of the 5 moles of oxygen, you can see I've got 5 moles of oxygen here. I've got 3 are used to make CO2. So there are 3 moles of O2 being used there. Effectively, we've got 4 O atoms left to account for. That means that we must have a 4 in front of here. So 4, that means that our oxygens are balanced. So I've got 10 oxygens on this side and I've got 10 oxygens on that side. So my next step, I just balanced it. Now, because I've got a 4 in front of the hydrogen, hydrogen only appears in one compound on the left-hand side and one compound on the right-hand side. So if that's a 4H2, that means I've got 8 hydrogens on this side. That must mean Y must be 8. So we've got C3, H8, and then all the other information that we know. And I think that's going to get us very close to where we need to be, if not where we need to be with this. Straight away, I can see that the ratio, this is the smallest whole number ratio, C3H8. They're asking for the empirical formula, so I need to check always. But that is the smallest whole number ratio, C3H8. I can't reduce those numbers any further down. 8 is not divisible by 3, etc., etc. So that is my answer.